Good. So we are recording now, and I am going to start sharing the screen. Let's take a look at the Canvas. No, first let's take a look at the syllabus. Syllabus. Right in here. Today is May 4th. We finished covering, oh, wait a minute. Our lab 4 due, right? Wait a minute. Yeah, I made lab 4 due today, right? Since lab 3 was due a week ago, I extended the due date of lab 4 for today. And then we have to start chapter 26, mirror and refraction 1, and here's gonna be mirrors and refraction 2. Let's take a look at the Canvas website, make sure everything is up to date there. Canvas. Courses. Lab 4 due today, 11:59 p.m. And we want to find out how the modules. Let's see here. The lecture 2026. Let's see if I have uploaded the latest one. Lecture and lab videos. 29th of April was last Wednesday. Okay, so we have everything uploaded for the videos. Now let's see the notes. I'm quite sure I also uploaded the notes. Okay, here we go. 174 pages, right? And yeah, so the notes is uploaded as well, have been uploaded as well. And let's now take a look at the book. And before we go to the book, let's take a look again at the exam, right? When it's due, it is Wednesday, the 20th of May. Let's see how we have 2 weeks and 2 days. 2 weeks and 2 days, we're getting there. We are on we finished chapter 24. Let's see what chapter 25 is all about. There must be a reason why I skipped it. Wiley? This one. Wiley. One more student coming in. Launch. '24. Let's remind. Oh no, it's not. We're not skipping 25. We are doing mirrors. Okay, so let me just update it here. Mirrors 25. Hopefully we'll be able to finish chapter 25 today because it's a very short chapter. Chapter 26 is refraction. Okay, reflection of light, mirrors. And then we have chapter 26, refraction of light, lenses, and optical instruments. It's a very interesting chapter. And let's Mirrors1. Let's see if we can finish mirrors today. Okay, and going back to the notes right here. Reflection of light by mirrors. That's what chapter 25 is all about. Insert a page break. Here is May 4th, 26. This is a Monday. And going back to the book. Electromagnetic. Yeah, we skipped Doppler effect and polarization. We just covered 24, 1, 2, 3, and 4. Let me copy and paste 24, 2, 3, and 4. I want also to make a list of the oh, here you go. We have all those sections for the exam 22, 23, 24 we have covered so far. So far, the material for exam 3 is plus labs 3 and 4. Okay, we're skipping those. What is in? Let me put only those ones that are showing up next. I'm going to put them in boldface. Everything else that's not in boldface. Okay, this one here, 22.6, we're skipping. And of course, we have to boldface the labs 3 and 4, right? Keep it consistent. Okay, so here you go. The theory we use for this chapter is very powerful. I have been able to file for patents just by using this theory of geometrical optics. We call it theory of geometrical optics. It treats the optics as though using geometry, which is one of the easiest topics in math, right? One of the first things that we learn in math. And it's called, again, geometrical optics. There are other approaches to optics. There are other approaches to optics that is far more powerful, but more difficult to understand, okay? One of them is called wave optics. Wave optics theory. If we have time, we're going to cover that. And then there are others that I'm not going to mention here. But like I said, geometrical optics is not as powerful, but it's very intuitive. Geometrical optics is not as powerful, but it is very intuitive. And the mathematical treatment is simpler. Mathematical treatment is simpler as well. In geometrical optics, we represent light as though as not as an arrow, but let's say as though as it is a line propagating along space. Okay, a line with an arrow, right? A line with an arrow at the end, propagating in space. This arrow shows the direction of propagation of the light ray that coincides with the direction of the pointing vector that we saw in the previous chapter. What for mirrors and other types of materials, optical materials, right? Optical materials, an incident light ray, we call it a light ray, is reflected at an angle equal to the incident angle. This is the so-called law of reflection. Let's write that down here. It's not exactly a law. Law of reflection. Law of reflection. The angle of reflection of a light ray is equal to the angle of incidence. This law can be proven using the principle in optics called the principle or law or postulate. Okay, they are all the same. They're all synonyms. Law, principle, or postulate, called the principle of least time. This law, and let me put again between quotes, the law of reflection is not exactly a law. They just give it a name, you know, it's a consequence. Remember, when I put everything under quotes, that's because it's not exactly a law per se, okay? Explicitly speaking. What is a law is the principle of least time. That is a law, a real law. That's a real law. Let's see. Okay, and I already mentioned that here. Okay, so light rays obey this principle. Light rays are always in a hurry to get to its final destination. Okay, I'm talking about hurry. Okay, to get to its final destination. In other words, this destination. Light rays want to go from one point to another one in the least amount of time, not in the least amount of space. Okay? That's why it's called the principle of least time. It's not principle of least distance, right? Or least space. Not principle of least distance or least space. See the difference? Always, light rays are always in a hurry to get to its destination. Remember that. And remember the pointing vector, right? For the case of the pointing vector of the pointing vector and light rays alike, comma, the electric and magnetic fields, of the light ray, electric and magnetic field vectors of a light ray is always perpendicular to the direction of propagation of the light, right? Which, by the way, is an electromagnetic wave. Always. We showed that before. Electric and magnetic fields are perpendicular to each other, and they are also perpendicular to the pointing vector, which coincides with the direction of propagation of the light ray. And so a principle, consider the following. In principle of less time, okay, we're going to start for mirrors. We're going to start with the simplest type of mirror. We're going to start with the planar mirror, so you can appreciate how we can start predicting how a light ray behaves whenever it is reflected by a planar mirror, okay? In the principle of least time, consider the following. In the principle of least time, consider a planar mirror, which is the simplest type of mirror, we have. Point S, from which is the position of the source of a light source, right? Of the light source of the light ray. And point P, the position where the reflected light ray from the source passes through. I'm going to draw that for you. In physics, we do very simple drawings, so you don't have to have this specific skill of drawing fancy situations. Illustration right in here. Magnetic electromagnetic reflections and mirrors. Reflection and mirrors. Okay. And the situations like that. Here you go, the pointing vector. Here is the plane perpendicular to the pointing vector. Okay. Here's this plane makes a 90-degree angle with the pointing vector, and the pointing vector makes a 90-degree angle both with the electric field and magnetic field, which are perpendicular as well. Okay, if we look at this plane sideways, right in here, okay, we have something like that. We have the plane that you saw before, the electric field, the direction of propagation of the light ray, which coincides with the pointing vector, and the magnetic field in blue color. So everything else that you see here are other planes that coincide with the electric and that contains the electric and magnetic field elsewhere of the light ray, okay? So here you go. For a point source, we describe the point source as an S. This point source can be an LED, can be a regular light bulb, can it be even the sun or any star. We draw the propagation of the light rays as arrows that comes out from the source. Okay, and that's a point source. If we're talking about a distributed light source that has a physical dimension, we would describe it somewhat like that. The light ray is propagating perpendicular to the not normal, right, to the surface of the light source. And here is my planar mirror. That's how we draw a planar mirror. We draw with those lines in the oblique direction, just to emphasize the fact that it is this surface here to the left that's reflecting the light. Okay, not this surface to the right. This right side here doesn't reflect the light, only the left side of this mirror. Now consider a point source, S, and a point. Let's see what's going on here. Let's see what's going on. Okay, it's a little dirty here in my screen. Next one. And then a point P through which the reflected light is going to pass. Okay. Okay, strictly speaking, if you were not for the principle of Lestang, we could theorize that the path of the light ray could have been any path. Could have been this one here, could have been this one here, could have been this one here, right? And so on. But nature doesn't choose this path. Nature does not choose this other path here either. Light rays or nature, they choose this path ray here that is stated according to that law, right? Law between quotes, law of reflection. What does the law of reflection state? The law of reflection states that the angle of incidence of the path ray is equal to the angle of reflection of the path ray, and this angle is measured with respect to the normal, to the reflecting surface. Okay, this. Let me get. I'll leave this way, and what I'm gonna do here. I'm going to draw a 90-degree angle. This guy is going to be sent to the back, right? And I'm going to put a little dot there inside, a black dot. To emphasize the fact that this angle, the angle between the surface of the mirror, makes a 90-degree angle with the normal to the surface. In this specific case, the normal coincides with the perpendicular direction. The normal coincides with the perpendicular direction because we have a planar mirror. You're going to understand what is the difference between perpendicular direction and normal direction, right? So let's take a look at this other one here, this other case. Here you go, the incident, the angle, the light rays. This is another situation. This is another light ray. This point source that you saw right in here emit light rays in every possible direction, right? And here is just one possible light ray that this light source is emitting. It is incident at the surface of the planar mirror at an angle. Here you go. The normal to the surface is perpendicular, right, to the mirror. And this light ray is incident as this surface with an angle of incidence, theta incidence. This theta of incidence is measured with respect to the normal. And again, it's very simple to memorize this law of reflection. The angle of reflection is equal to the angle of incidence. Another light ray coming out from the source the normal at that point, which is perpendicular, right, to the surface of the mirror, and again, the angle of reflection is equal to the angle of incidence. And we have another one here, angle of reflection equal to the angle of incidence, etc. Okay? Can you picture that, right? And what we are going to do now, we're going to locate, let me write down, I think I already wrote that down here, right? So here you go. In the principle of least time, consider the following: a planar mirror, point S, which is the position of the light source of the light ray, a point S, a point P, which is the position, where a possible reflected light ray from the source passes through. And you have to consider to another thing, right? Consider the following: the direction normal to the reflecting surface. If the reflecting surface is a planar mirror, comma, the normal surface will also be perpendicular to the surface of the plane of this planar mirror, of this mirror. I'm not even going to repeat it, right? Of this mirror. The normal direction would be the normal direction. The direction, okay, no, keep it like that. The direction normal to the reflecting surface. Now you already know what's the normal direction, right? And, oh, actually, let me, by normal direction is defined as the direction perpendicular to a surface that is tangent to the reflecting surface. And normal direction is defined as the direction perpendicular to a surface tangent, okay, to the reflecting surface. For a planar mirror, okay, this normal direction is perpendicular to the surface itself, to the reflecting surface itself, since its tangent coincide with this surface. Now let me give you another example of a more generic example. Let's see if I have it here. It is slide 23, well, 22. We're going to go back to that, right? Okay, here you go. I'm going to show you an example of a normal surface, okay? Consider now not a planar mirror, but consider a spherical mirror. Consider a spherical mirror. And we're going to section this spherical surface with a hub, right? We're going to end up getting a hub here, the section of a sphere. Here you go, a hubcap, just like a hubcap of your car, of your tire, the tire of your car. Here's the tangent to the spherical surface. the tangent surface to the spherical surface. Does not coincide with the surface, right? Because it's a more generic surface here in this case. And the normal direction, what's going to be the normal direction? The normal direction is going to be that direction perpendicular to this tangent surface. To this, okay? If we consider this other direction right here, we have to draw another tangent surface at this point. I'm going to draw that with a different color. And now you should have a better idea the difference between normal and perpendicular. Here you go. Another normal surface. Another tangent surface. Let's see, one surface tangent to a given point, to a given point of the spherical surface. And then here, another surface. I'm gonna put it in the red color. Another surface tangent to a different point of the spherical surface. So now you should have an idea what the difference between normal and perpendicular, right? Going back to 22. Okay, and now here you go. In geometrical optics, we usually want to draw the position, not just the position of the source, but also the position of the image that's formed behind the mirror. And there is a specific technique that we have that works very well. There is a specific geometric technique that we use to do that. Okay? So let's write that down here. In geometrical optics, we usually want